this. I've already learned this before because it's truly the beginning of your exponential algebra, exploring exponential models. And what we're going to do today is some basic graphing. We're going to talk about what exponential growth looks like, what exponential decay looks like, and that'll probably wrap it up. So our objective is going to be to model exponential growth and decay. And exponential growth is something that happens all around us all the time, and we don't even think about it. And that's going to be any bad bacteria. And especially over the last few weeks when everybody has been so sick, the whole problem with bad bacteria is that it grows much faster than good bacteria does. So you go to get a strep test, they wedge that thing in the back of your throat, they put it in a petri dish, and what they do is they watch its growth for a short amount of time, and they try to figure out, hey, is this bad bacteria or good bacteria? And then every once in a while it doesn't start growing like right away, and you'll go home and they'll say, well, the early strep test said you didn't have it, but you'll get the call the next day. Oh, now it did, because when they watched it overnight, all of a sudden, boom, it's filling up that petri dish. So exponential decay would be hopefully what happens when you get the antibiotics, and kind of kills off that bad bacteria and it starts dying off. It's also what happens as they try to figure out how long something has been, well, this is morbid, but dead, They use that carbon dating in order to figure that out, and different measures that they can use to measure that decay. But both of those things are going to be exponential. So I'm going to model exponential growth and decay, and this one says we are to move the stack of 5 rings to another post, but there are rules. A move consists of taking the top ring from one post and placing it on another post. So your first move obviously is to grab this little one and put it on one of the other posts there. And you can move only one ring at a time. Can't grab a couple of them. Do not place a ring on top of a smaller ring. So now the rules are getting a little bit more involved. And it says, what's the fewest number of moves needed, and how many moves are needed if you had 10 rings, 20 rings? Explain. So it takes longer than we think it does, and it just happens that this is going to be an exponential relationship. And we're not going to spend a whole lot of time on it, but what I wanted to show you was that originally it would take 31 moves to successfully make this work. And obviously if you messed up, it would take more than 31 for you to go back and fix it. And then if we get to 10 rings, now it's going to take 1,023 moves in order to make that happen. And at 20 rings, now it's going to take you 1,048,575 moves to make that happen. I don't know about you, but I kind of get bored with Monopoly after a while. I don't think that's going to happen for me. I'm going to be giving up after a little while. So the moves here are exponential. Now, how do I know that? Because you can't simply multiply 31 by something to get 1,023 and multiply by the same thing again and get 1,000,000. This thing is really growing. It's really happening fast. So that's an exponential relationship. So down here what we're going to do is we are just going to graph some exponential functions. And it says, what is the graph of y equals 2 to the x? Which, by the way, is the parent function for exponential growth. Maybe you already remembered that from your exponential algebra class. Now, why is that the parent function? Because in order to have exponential growth, your base has to be a number that's bigger than 1. That's what makes it bigger. And if you think, well, what's the first nice number that's bigger than 1? 2. That's the first one. So that's going to be exponential growth. So what we're going to do is we're going to take 2 to these powers. So 2 to the negative 4th, they start thinking, okay, well, that's going to flip it. So that'll be 1 over 2 to the 4th. And 2 to the 4th is 16. So this is going to be 1/16, kind of a small little fraction there. To the negative 3rd, I'm going to flip it. So 1 over 2 to the 3rd, that's going to be 1/8. 2 to the negative 2nd, flip it and square it, 1/4. 2 to the negative 1, flip it, 1/2. Anything to the 0 power is 1. 2 to the first, 2. 2 squared, 4. 2 to the third, 8. That's my basic parent function right there for exponential growth. So we're going to get these points on here. And if you're graphing like I am up here with this big thing, I'm thinking I'm not going to be able to even tell the difference between 1/16 and 1/8. You know, there's not enough room up here for me to space that out. So I just have to make it really low and close to 0. And then at -3 1/8, like I said, it's not going to look a whole lot different than my 1/16. Try and put it just a teensy bit higher. Then -2 1/4, -1 1/2. Now it's starting to get where my graph is going to be a little more accurate. 0 1, 1 2, 2 4, and 3 9. Oh, sorry, 3 8. 1 too high. Oh, there we go. And then, like it says, we're going to plot and connect the points. So I have a problem. I don't know how far down to go with the left part of this graph. So I have to think about this a little bit. It went from 1/2 to 1/4 to 1/8 to 1/16. So the next one would be 1/32, 1/64, 1/128, 1/256. Am I going to get to 0? No. I'm going to get super duper close to it. In fact, you know, you probably won't be able to tell. I mean, if I'm trying to do that just a little bit higher than 0, it kind of looks like 0. But it's never quite going to reach 0. So we have to make sure that our graph looks like it's going to approach 0, but it's never quite going to cross it. And that, in fact, is called an asymptote. When you have a line that you're going to approach, but you're never going to cross. So our asymptote for this graph, that's spelled like this, would be y equals 0. Because y equals our horizontal lines, and the x-axis is y equals 0. So what this shows us is exponential growth should look like that. You should be starting low on the left-hand side and then increasing as you go to the right very quickly because it's exponential. It's supposed to grow really fast. So there's our basic parent function for exponential growth. But notice they're changing the base now. This one says, how about y equals 4 to the x? Well, that's still going to be growth because it's a number bigger than 1. The 4 is a number bigger than 1. In fact, it's going to grow faster than the last one. But I'm not doing all those points they had on there before. Maybe I'll just do -2, -1, 0, 1, and 2. That should be enough to get a feel for it because all of those graphs have that same basic shape. Shelby, please put the phone away. 4 to the -2. Okay, negative is going to flip it, and then I have to square it. So 1/16. 4 to the -1, -1 is going to flip it. 1/4. 4 to the 0 is 1. 4 to the first is 4. 4 squared is 16, and yeah, it's going up really, really fast. So let's go down here and get y equals 4 to the x graph. So at -2, we're really, really close to the axis. That one's supposed to be 1/4, 0, 1, 1, 2, 3, 4, and then we're already up to 16. Looks like I need to orient my smartboard. It's a little too high, perhaps a little too high. But there it is. It looks a lot like y equals 2 to the x. It's just going up faster, that's all. And getting closer to 0 faster on the other side. But its asymptote is still the same. Still y equals 0. And I think it's kind of interesting that for both of these graphs, when we raise them to the 0 power, they're both 1. So that meant 0, 1 was on both of these graphs. Well, we're going to find out that's a nice little helper thing that we get from these growth and decay models as well. That if we put a 0 in there, we get a 1 until there's a number in front. And that number in front is going to be an A value, which we dealt with before. Now B is different. This is definitely different. That can't be growth. 1/3. That's a fraction between 0 and 1. That's not growth. This is going to be decay. Exponential decay. So this will be an interesting graph to look at because it's going to be different than the others that we just did. So we'll try again with our -2, -1, 0, 1, and 2. Okay, it's a fraction. And now I have to flip it because it's negative. So it's not going to be a fraction anymore. It'll be 3 squared, which is 9. Then we've got 1/3 to the -1. Well, that's just flipping it. That's going to be a 3. Anything to the 0 power is 1. All 3 graphs, that's happened. First power, 1/3. Second power, 1/9. You square both the top and the bottom of the fraction. Okay, it's backwards. We've got all the high numbers on the left-hand side and all the low numbers on the right-hand side. So let's graph that one. -2, 9. -1, 3. There's that 0, 1 again. And we've got 1, 1/3, and 2, 1/9 again. They just are going to look really small. Oops. So it's still going through 0, whatever we have for our base value. Did the asymptote change? No, still the same. Still y equals 0, but definitely decay. Started high and went low. All right, there's one more up here. This one says y equals 2 times 3 to the x. Okay, let's see. Well, the base is a 3. That's what's being raised to the power. Going to be growth. But whatever I get here, I have to multiply by 2. So this is going to go up even faster. 2 times 3 to the x. So, might not need a whole lot of numbers for this one. Let's try -2, -1, 0, 1, and 2. If this is going up really fast, it might be flying off our -10, 10 grid pretty quickly. All right, -2. Have to flip the 3, so it'll be 1/3. Square it, that's going to be 1/9, and take it times 2. Okay, Cedar, do you expect us to do all that in our heads? No, you've got graphing calculators. You could punch it in. Punch in 2 times 3 to the -2. Let the calculator do that if you want. To the -1 power, flip it. 1/3 times 2, 2/3. Put 0 in. Now remember, with all the other graphs, I got 0, 1. If I put 0 in, 3 to the 0 is 1, and 1 times 2 is 2. So I have to wonder, where was the 1 in all of these other graphs? I mean, if this one came out 0, 2, pretty obviously it's supposed to be the number that's out in front. Oh, if there's nothing there, there's a 1. That's where it came from. That's why all of those are giving us that. We put a 1 in here. 3 to the first is 3. 3 times 2 is 6, because we always follow the order of operations. Powers first, then multiply. 3 squared is 9. 9 times 2, ooh, that is way off our grid there. But we'll graph what we have. And we got -2, 2/9. And we've got -1, 2/3. 0, 2, because that was our A value. 1, 6. And then 218 is way off the grid. So we're just going to make this look almost like it's going straight up and down. Right there. Now, I think about what that 2 meant in the past. The 2 out in front meant it was a vertical stretch. That's what it's doing. You know, if we grabbed these graphs, actually this one back here, and we pulled it up, it would match this one. You know, it's just what we do. So it's still a vertical stretch. But notice again, the asymptote, gotta spell it right, we're still not crossing that x-axis. Interesting. So I think ahead. What would make that happen? I'm thinking about something that would make it go up or down. What's going to make this go up or down? Think about A, H, and K. Which letter would help us move this up or down? K. So K is going to tell us whether or not we get a new asymptote, because this has to move up or down as we go through it. So some basic exponential graphs there. And like we see here, you know, exponential functions do model all kinds of real-world stuff. Half-lives. You'll hear how medications have a half-life. A lot of different things have a half-life. But what it means is they lose 50% of their potency. And that's why they put the expiration dates on bottles, is to let you know, okay, over time, this isn't going to be as useful as it was to begin with. And in fact, at this point, it's half of what it should be, so it's not going to help you out very much. Radiometric dating, that's that carbon dating, interest-bearing savings account, population growth, and not that we want to really study a bouncing ball, but yes, you can use a bouncing ball as an example of exponential decay. So on the next page, we get this great big pile of kind of a mapping diagram here to show us what's going on. And an exponential function at this point is going to be y equals a times b to the, with a little x there, where a is not 0. Because if it's 0, then we're graphing y equals 0, which is the x-axis, and that doesn't make any sense. So if the base is greater than 0 and it's not 1, we're just going to think, okay, is it bigger than 1? Then it's going to be growth. Is it a fraction between 0 and 1? Then it's going to be decay. B is a constant, and x is called the independent variable because that's the one we get to pick. When we made our table, we put x's in and we got y's back out. So two things that can happen. We could get exponential growth. That's going to happen when our base is bigger than 1. Even if it's 1.1, it's still growth because you're multiplying by 1.1. It's going to increase it a little bit. And decay, oh, what is this little x doing here? That should be here. I think the smartboard did this last year too, and then I went and fixed it all, and now it's still putting things in response. Exponential decay, y equals a times b to the x, where what this really means right here is that it's a fraction between 0 and 1. When they say b is going to be greater than 0 and less than 1, yeah, it has to be. It has to be a fraction between 0 and 1. And with both of these, they're telling us the number in front is going to be positive. So we're not doing reflections yet. What we're doing is we're just looking at what's the shape of this graph. And here's our parent function for growth, y equals to the x. Our parent function, when we talk about decay, if you ask anybody what's one fraction you wouldn't mind working with, most people will say 1.5. It's just like divided by 2. So that's our parent function that we have for decay. Now, we are going to talk about those asymptotes. Again, it's a line that the graph approaches, but it's never quite going to get there. Like I was talking about when I said it's 1/32, then it's 1 over 64, then it's 1 over 128, and then it's 1 over 256. It's never going to get to 0. We always have another number that we can divide by 2, so, or multiply by 2 in the case of the denominator. A line the graph approaches as x or y increases in absolute value. The y-intercept, always going to be 0a. That's kind of nice. And that would be one really nice point that we can get for all of these. And then our domain, we can put in whatever numbers we want. All real numbers, you can make the symbol with the R with the extra line if you want. Or we're going to put in whatever we want there. But we don't get all y's back. For the ones that we were just graphing, we never went below the x-axis. So our y's were greater than or equal to 0. In this case, they're going to say y is greater than 0 because we want to get to that asymptote piece where we're saying, hey, it's never going to approach it. Now, if we have a k value to move it down, then that's going to change. But for right now, with no h and k, y is going to be greater than 0. Now, we're going to talk a lot about interest because the MCAs love problems about savings accounts and bonds and all that kind of stuff. So, if you're having a savings account, it's going to increase by a fixed percent each time period. And they'll tell you usually it's going to be quarterly. Most banks will do quarterly interest. And it could be that it's going to decrease by a fixed percent each time period. As you get older and you decide what you want to do, some of you might decide you're going to run your own business. Years ago, I had a student who, his dad had a whole bunch of old lawnmowers and he used to spend all this time fixing them up. And he went into landscaping, had his own landscaping business. And when you do that, you have to have a computer. You have to be able to keep track of all your business and make receipts for people and all that good stuff. And so one of the things that he had to do was he had to depreciate his computer. It used to be that computers, the very first year that you bought them, you could write off half of the cost of your computer the first year on your taxes. Now there's a fixed percentage that they use for writing off that as a business expense. So decreases by a fixed percent each time, usually going to be depreciation. Something's depreciating. Now this says A of t is the amount after t time periods. Little a, lowercase a, is going to be the initial amount, and little t is going to be the number of time periods, because we need formulas. If we're going to figure this stuff out, we need formulas. And the first thing I notice about this formula is it has a plus. That means things are going to get bigger. They're adding. R is going to be the percentage increase as a decimal, because whenever we use percentages in our math formulas, we have to move the decimal over two places and use that for the math. B is called the growth factor, and that growth factor is 1 plus R. Wait a minute. Before they told us it's y equals a times b to the x. And now this is on that same chart. Yeah, because this is b. It's what's being raised to the power. So it's still y equals a times b to the x. The difference is we're probably not going to graph this. Instead, we're going to talk about how much money do you have at the end of 5 years. You know, we want to know what is the payout. And over here, we notice subtraction. Again, that is b, right there. So if I have 1 and I subtract my 2 decimal percentage, well, I really do get a fraction between 0 and 1. It's going to be a decimal, but it's a fraction between 0 and 1. So what I use there for R is my percent decrease. If they say, you know what, you can write off your computer, the new tax laws say 20% every year. Well, then I need to make sure that I put 1 minus 0.2 in this formula and calculate it for how many years I own my computer. B is called the decay factor, and that's going to be 1 minus R. That's our base. So definitely a decimal between 0 and 1, which makes the fraction between 0 and 1. So that's a big summary of all the wonderful things that we're going to do with exponential growth and decay. And on the next page, we just get started. It says identify each function or situation as an example of growth or decay. And then what is the y-intercept? All right, well, we have to figure out whether or not they added something to the base so that it's bigger than 1. Then there'll be growth. Or if they subtracted something so that it's a number between 0 and 1, then it's decay. And once we've done that, they want us to tell them 0a, because this is the y-intercept. Remember, to get the y-intercept, you set x equal to 0. It's always opposites when you talk intercepts. So y-intercept, x equals 0. All right, let's look at A. It says y equals 12 times 0.95 to the x. That is my base. Is that growth or is that decay? Got to be a number bigger than 1 to be growth. Is it growth or is it decay? It's decay. In fact, they subtracted 5%. This 0.95 is 95%. We started with 100, we subtracted 5%, and we got 95. And then all we have to do is give them 0, A. Well, this is A times B to the X, so that's going to be 0, 12. There's the y-intercept. Let's go over to B. That has my attention right away, because that's the base. Is this one growth or decay? Growth, bigger than 1. So what they really did was they had 100%, which would have been a 1, and they added another 100%. So that gave them 2. So we've got a 100% extra growth here. And then we need our 0A for our intercept. What's A? .25. There it is. Remember, it's A and then the base raised to the power. C says we're going to put 1,000 smackers into a college savings account for 4 years. The account pays 5% interest annually. Wow. We want to know how much we're going to get. This is an adding problem. It's a savings account. You know, you're supposed to get more money when you're done. Aslan put the phone away. A. A is the initial amount. How much are we putting in the bank? $1,000. Did they tell us the interest rate? 5%? Okay, we can't put 5 in there though. What do we put in? 0.05. T stands for time. Did they say how many years? 4. Well, we'd follow the order of operations and add these two together. But then in the end, we'd grab the good old calculator and figure out what we have. So if you don't have a calculator, it's okay. I'll punch it in up here and you can watch. So we have 1,000 times 1.0524. So $1,215 and 51 cents. Here's the reality. Banks always round down. So you'll get $1,215.50. But the answers in the back of the book should match just normal rounding. Alrighty. Down here, we have some guidance using the same stuff. And good news, the clock is with us today, so I can do candy partners. So go ahead and get started on these, and I'll get you a candy partner, and we'll see if everybody's picking up on all the pertinent information here. I think there's a couple of groups that are just kind of finishing up their conversation about C down here. But what did you get for A? Is that one growth or decay? Growth. Y-intercept? 0.3. How about B? Okay. And Courtney had a really good question. I just didn't even think they had done any of that in any of these, but they put the X in the parentheses here instead of outside. It doesn't matter because when we do, please excuse my dear Aunt Sally, the order of operations, we're going to have to do exponents first anyway. So it doesn't matter if it's in the parentheses or outside the parentheses, we have to do that part first. This one is 0 what? 11. And then we had use that little y equals a times 1 plus r to the t because it's a savings account. You're supposed to get money. That's what the plus is telling us. And we're going to put a 2,000 in here times 1 plus 0.06, changing that into a decimal from that 6%, and then slapping that into the calculator. And let's see, what did that one come out to be? First of all, they did just want to know that this was growth, but I do know that a lot of you went ahead and did the math, so we'll make sure your math is right. This is growth, and it would go through 0, 2,000 for that y-intercept. But yeah, I'd be more interested in what are you going to get. you'd get $2,524.95. That's what you'd get. But the key there is knowing you're getting something, which means you use the formula with a plus. You're not losing something. You know, car depreciation is one of those that's huge. You buy a new car, you drive it off the lot, instantly it loses thousands of dollars. Why does it do that? That's not fair. Because now if they go back to sell it, they have to say it has had one owner. Before they could say it's never been owned. Nobody has had it. Now it has one owner. Even if you brought it back after a month, it's got miles on it, it's had an owner, you don't know how they've driven it. So depreciation is one of those things that we don't like it. But it happens. It just does. The value of most things will drop over time. Antique stuff, hey, that actually should gain value over time. So this next page, what I want to do is go over a couple of these with you and then let you and your partner go through. Because what we want to do is identify these as growth or decay, and then we want to give the percentage of growth or decay. So that's new for us, not the growth or decay part. Take a look at number 1. Is that one going to be growth or decay? Definitely going to be decay. That is a fraction. 34/100ths is a fraction between 0 and 1. But their question isn't, you know, what's 0a and all that. It's, well, what was the percentage? So I realized, well, this came from something minus, I should say something minus 100% minus something gave us 0.34. Now, most of the time we don't set up the algebra equation because 0.34, we can think in terms of money. So most people would say, okay, if that's 34 cents, that means they took away 66 cents. So it was actually minus 66%. And just kind of do it the thinking way through there. Now you absolutely could set this up, subtract 1, divide by a -1, you're still going to get 66%. But it's going to look like this, 0.66. And we want that as a percentage. So it's 66%. This one over here, number 2, growth or decay? Growth. Now it's growth because it's 1 plus something. So you could certainly set it up with algebra if you need to, but most people are going to look at that and be able to tell me the percentage growth right away. How much did they give us? 5%. All right, so go ahead and do the rest of this page with your partner, growth or decay, and figure out what that percentage is. What did they take away or what did they add? Number 4, growth or decay? Decay. That is 6/10. That's a fraction between 0 and 1. So whenever these have 1 or 2 digits, I always think in terms of money so that I don't have to write an equation. I think, okay, I had $1, now it's 60 cents. How much did they take away? 40 cents. So, whoops, missed my 0. So they took away 40%. Remember, we moved the decimal over 2 places. Now, for number 5, most people are probably grabbing a calculator for this one. Is this growth or decay? That's definitely decay. I mean, we've got tenths, hundredths, thousandths, 10,000ths, 100,000ths. 2,125 100,000ths. That's definitely a fraction between 0 and 1. But then what we want to know is, okay, if I had $1 and I subtracted this, that's what they did. They took off that amount. So if we just take 1 minus 0.02125, we'll get our percentage, 97.875%. Again, you can write the equations like I showed you earlier, or you can just think backwards in terms of money. 6, growth or decay? Growth, quite a bit of growth. And a lot of people wrote down 2, but remember, you have to move the decimal back 2 places. This is really 200% because they added 2 to the factor, but they had moved the decimal over 2 places to get it there first, so 200%. 7, growth or decay? Growth. And you ask yourself, well, how much above 1 is this? 0.875. above 1, which would be 87.5%. Then is H growth or decay? Decay, and lots of it, because I had $1 to start off and now I only have 2 cents. How much did they take away? 98%. Shoot, I was looking at the regular bell schedule. Doggone it. If you need to, take a picture, otherwise I will save the completed notes on Schoology. Tuesday's schedule got me again.
Snap one. Just snap it to me.
After all this time, I'm still surprised when the bell rings on Tuesdays. Like I said, take a picture if you need to with your camera, or it'll be on Schoology. Skip it around, get a few of these, a few of those, and a few of the others.
No.
Alrighty.
Cedar Falls.
Hey, how you doing, Benjamin?
I'm tired.
Yeah, I know. Take care.
Got some good stuff. Sorry.
Okay.
There you go.
Thank you.
Okay. Yeah, you too, Caleb. Oh, and I forgot to start the